confirmed with
the specifics of what I'm going to talk about is that I want to be creating instanton-like vertices or small instanton events in the course of a scattering process in QCD. This allows me to cleanly separate from the complicated infrared physics where semi-classical approximation which instantons are based perhaps is not valid, right? So it would be the partonic energy, right, underlying the scattering event, which would be selecting the instanton size. And I would not let this partonic energy to go anywhere below 30 or 20 GeV. So I'll stay in the regime, in a controlled regime where the coupling constant, where the strong coupling constant is not too strong, right? Maybe about 0, definitely not greater than 0.4, 0.3, right? And then can go to the weakly coupled regime. So interestingly enough, we'll see that the instanton cross sections, or for cross sections for instanton dominated processes, let's say at LHC energies, can be very large, right? So instantons probably are there. The difficulty comes in with still distinguishing these instanton generated effects from the QCD backgrounds, and this is a tough problem which is being investigated right now. Okay. So first, a quick reminder. So about QCD instantons. So you all know that instantons correspond to instantons in any non-abelian gauge theory correspond to tunneling events between the different winding numbers. Between the vacuum with different winding numbers, insofar as semi-classical approximation is valid. What is specific about QCD, let's say, compared to the electroweak theory, that the barrier between the different vacuum states, which we would normally call the sphaleron, does not exist in QCD at classical level, right? So there is no web of the Higgs because there is no Higgs. And so the top of the barrier is something which is set by the quantum effects. And we'll see in the course of my talk of what will actually do it. And why is it important? Because this is this barrier is essentially something which cuts off the integration over the instanton size. Good. So when the kind of quintessential process, the classic processes I would be looking for at the partonic level, let's say, is when I have two gluons, so actually any two partons in the initial state. So let's start with the two gluons in the initial state. They can produce an arbitrary number of gluons in the final state plus an F quark-antiquark pairs with specific chiralities. And F here is a number of light flavors. So the flavors with the mass which is smaller than inverse instanton size, right? An important thing is that this number of gluons is not fixed in the instanton process, and at sufficiently high energies, this number can be very large, yeah? Can be non-perturbatively large, of order 10, 20, and so on. Good. So, so the process, so this is a process we are looking for. So you can similarly have process initiated by the two quarks in the final state, so quark-antiquarks, not in the final, in the initial state. And so these are all the processes we can look for. So how do you compute an amplitude, right? How do you compute an amplitude which is dominated by an instanton from a two-particle initial state, let's say two gluon initial state, to n gluons plus 2nf fermions, right? So you perform and you compute the amplitude by looking at the path integral, right? Looking at the path integral dominates the path integral in the instanton, right? So you basically repeat the classic Toft analysis where you integrate over the instanton collective coordinates. There is a contribution from the instanton determinants. There is a so there's an integral over the instanton position, instanton size, instanton density, e to the minus instanton action. So as I said, determinants are also present. And then you are looking for a particular amplitude which has, so in this case, n plus 2 gluons, so for which you put in the n plus 2 gauge field configurations, Fourier transformed to the momentum space, and LSZ amputated, right, and you basically substitute the instanton configuration there, the instanton field configuration there, in the leading order instanton approximation, and then you put 2NF fermion zero modes, right? Again, in momentum space and LSZ reduced. And then we integrate over all of the instanton collective coordinates. So in the leading order instanton perturbation theory, right? And by leading order, I mean that all of the incoming and outgoing legs have the actual instanton configuration in it, rather than fluctuation around the instanton configuration, right? So in the leading order, the instanton vertex just looks like a multi-leg. So the instanton process corresponds kind of like to a new non-perturbative vertex in perturbation theory with a large number, namely n+2 gluon and 2NF fermion legs, and it is perfectly spherically symmetric. So there is no correlation between the different legs of different momenta, right? So if I wanted in perturbation theory to produce a vertex with a very large number of external legs, I would have basically, it would only be possible by having quite an extended Feynman diagram with propagators connecting, internal propagators connected in a complicated way, all the external legs, right? And this vertex would be highly correlated and not essentially spherically symmetric. So when you look for one of the key points of how to look for the instanton generated amplitude at colliders, the triggering event would be to look for this spherically symmetric vertex in the center of mass energy, involving large number of external particles. Looking for chirality violation at colliders, that is very difficult. That's not a practical thing to do, as far as I know. Good. So the actual approach we are going to take. So instead of computing the scattering amplitude, right, with 2 to n scattering amplitudes and then squaring it, I will look instead for basically would apply the optical theorem and look for an imaginary part of a forward elastic scattering amplitude dominated on the instanton anti-instanton background, right, like the picture is shown here, right? So the actual 4-point amplitude, which I'm going to cut, that is take imaginary part, would be then computed on the instanton anti-instanton background. And what's good about this approach, is that this approach automatically takes into account all the complicated rescatterings between final state particles, right? So all of the interactions between these intermediate lines, which are cut off here in the forward elastic scattering amplitude, are automatically taken into account by instanton anti-instanton interaction. So I don't need to bother myself with that, right? And then interactions involving initial hard particles will be taken into account in addition, right? So this is approach which was first used by Ringgold and myself in '91, applied to the electroweak instantons, and so here we are going to use it for QCD instantons. The actual instanton anti-instanton configuration is defined following what's called the Valya method, and that was invented by Jung somewhere in the late 80s. Good. So basically, we come back to the path integral interpretation of it. So we say that the total cross section now is 1 over S imaginary part of Minkowski space continued Euclidean Green's functions LSZ amputated, and now it has two instanton gauge configurations in the initial state, 2 instanton gauge configurations in the final state. We have some so the instanton determinants are inside this instanton densities, d of rho and d of rho bar. Rho bar is the size of the anti-instanton. This instanton anti-instanton action in the exponent. There is a contribution K fermion which takes into account all the NF pairs of fermion anti-fermion states in the final state or intermediate state from the perspective of forward elastic scattering amplitude. Okay, and basically what happens is that the exponential suppression instanton anti-instanton action, right? So at infinite separations between the instanton anti-instanton, the instanton anti-instanton action is just twice the instanton action. But as soon as the distance r between the separation between instanton and anti-instanton gets reduced, the action is no longer that large. The action basically also gets reduced as I reduce the separation. And where is this instanton anti-instanton separation will be? Well, we just have to perform the integral, and it would be basically determined by the energy characteristics of the process. So the instanton anti-instanton action, as I described it, so on this instanton anti-instanton Valya configuration, has been computed in a certain approximation by Jung, and then Ringwald and myself, and then Werberschott in the early 90s. The exact derivation of it lies outside of this talk, but it's basically the shape of the instanton anti-instanton action, where chi is the distance between instanton and anti-instanton, and rho is some characteristic size. So let's say a geometric average between instanton and anti-instanton sizes. So when this variable chi, so when the instanton separation divided by the instanton size goes to infinity, the instanton anti-instanton action goes to twice the action of a single instanton. So it's 4 pi over alpha times 1. So the action is very large. And as the instanton separation goes down, the instanton and anti-instanton ultimately annihilate one another into perturbative vacuum. So of course, in this regime, when we are close to perturbative vacuum, this is not exactly a non-perturbative computation. So we are not cleanly separated from the perturbative vacuum. But in our case of QCD instantons, we actually will never have to get, because the kinematics will set up things in such a way that the dominant configuration would correspond to this variable chi being not too small, somewhere around there. So this non-perturbative approach, semi-classical approach, will still be justifiable. Okay. So this is back to our integral. So this is the expression for the instanton density, similar expression for density of anti-instanton. So kappa is a constant, and all the ambiguities and errors or whatever in this kappa described in the previous talk, well, they're not very relevant for us. They're inside this kappa. We will see that, well, this is the theoretical uncertainty we have. I would be happy if we have 1 or 2 order of magnitude normalization correct up to 1 or 2 order of magnitude. So effects of 10 or 20% are not going to be very relevant for me, but okay. I learned something from the previous talk. I'm going to check whether I'm using the right constants in determining this kappa. But again, for any practical applications, this would be completely irrelevant for me. Okay, and so now these are the 4 legs of but basically the 4 gauge fields computed on the instanton and on the anti-instanton, right? So if we carefully LSZ amputates, then what we are going to find is some certain factor surviving to the 4th power, because we have 4 legs. S prime, square root of S prime, is the partonic energy of the collision, right? So 1 over G factor is a familiar factor of the instanton, right? So each instanton goes as 1 over G. So there is some rho squared for normalization purposes, which naturally appears there. Then there is a factor of e to the IR P1 plus P2. So this comes from the fact that instanton was at position X instanton, anti-instanton was at the position X anti-instanton. So the difference between them is R. So the fact that there was an instanton and anti-instanton center picks up the factor of e to the IR P1 plus P2 in Euclidean space. So it basically takes into account the separation between instantons and anti-instanton. Now, if I had introduced a virtuality on each of these external legs, so virtuality Q, I would also pick up a form factor e to the minus Q rho plus rho bar. Whenever I introduce this, if I am to introduce this virtuality, which for most of the talk I will not do, I will keep it for the 1 GeV. So it's really not a very large effect. It's going to have very small consequences. But if you wanted to do it, so this would be there. And it all comes from just doing a careful Fourier transformation and LSZ reduction of the instanton legs. Now continuing this to Euclidean space, turns the imaginary exponent, which depended on separation, into the positive exponent e to the R0 square root of S prime. So where R0 is the temporal separation between instanton and anti-instanton centers in Minkowski space. Okay, so what we've got, and this is something which has been known since early 90s, and that was kind of a cornerstone, for example, of the calculation I had with Ringwald for electroweak instantons. So we have a positive factor, which depends on separation between instantons and anti-instantons and the partonic energy. So there's a positive factor in the exponent, and then there is a negative factor, which comes from instanton anti-instanton action. And it's a combination of these two, which will fix a dominant contribution for the instanton anti-instanton separation. But that's, of course, not the full story. Now, the instanton sizes. So if we were in electroweak theory, the presence of the Higgs wave, which in its own turn leads to the existence of Sphaleron on the classical level, will give a contribution to the instanton action of e to the minus, so instanton action of pi squared v squared rho squared. And that would cut off the instanton size. But we don't have it in QCD. So we have to include something new. Otherwise, these integrals are divergent. Now, let's think about why these integrals are divergent, right? So far we were doing everything at classical level, right? Okay, so we took into account the interactions between final legs of the instanton using this optical theorem approach, but it's still essentially a classical calculation. So QCD, of course, is a classically scale invariant theory. So unless I've taken into account quantum corrections, there is nothing which is going to set a scale at the classical level. So which quantum corrections do I need to take into account? So I need to take into account the dominant quantum corrections, the ones which are set by the partonic energy of the collision. So I'm treating the energy in the collision as a large parameter, right? It's a high energy collisions. So at the leading order contribution, right? So these little tadpoles describe classical instantons, right? So two are coming in and are coming out. So I have to now start taking into account quantum corrections, i.e. replacing or adding to this leading order contribution of two incoming instantons, of two gluon legs computed on the instanton background. I have to start taking into account propagators in the instanton anti-instanton background. So because this is a quantum correction, and then resumming all of them in the appropriate limit. So the limit is that each of the p squares is 0 or close to 0, and the square root of s, well, s prime, is much greater than one of the inverse instanton sizes. And this way you can resum perturbation theory. And you resum perturbation theory. So this was a leading order contribution in perturbation theory. These are high order contributions in perturbation theory. And Al Müller had carried out this calculation in 1991. In fact, for the case of QCD, not even electroweak instanton, this is a known result which hasn't really been used very much in the past, apart from the kind of qualitative level of what happens. And most of the reasons for it was because it was applied for electroweak instantons, where there are lots of other unknowns. So now we're going to apply it for QCD. So this contribution, so it's a term in the exponent. It has a negative contribution. It's e to the minus something. Now, because it's a resummed quantum correction, it goes as alpha over 16 pi. Yeah. So if I say, so it's a quantum correction, so it's not surprising it has a power of alpha. Doesn't mean that it's small. And then it goes as e squared. So e squared is square root of s. So it's e squared rho squared, right? So it's e squared is s prime times rho squared, and then there is an additional logarithmic enhancement with energy. And mu r is a certain renormalization scale, which actually is not determined by this calculation, but we'll sort it out later. Okay, so as advertised earlier, not surprisingly, quantum corrections lead automatically, right? So this is a calculation. This is not something which I input by hands, right? It's a calculation. It's a leading order. This is a leading order exponential resummation of this contribution. So it leads to an automatic cutoff on the instanton size. So at energy at high energies, right? So essentially, the rho squared cannot become much greater than 1 over e squared with appropriate powers of alpha in it. Okay, so this is how the calculation becomes. So kind of this is how a setup becomes completely, unambiguous, right? I don't have to try to figure out what cuts off the instanton size and put it by hand, so it is automatically there. There are, of course, potentially and most definitely present high order corrections somehow, but they are supposed to be, well, we don't know what they are, but they would be expected to be suppressed, would be subdominant in comparison to this one. So at the end of the day, that's the integral we have to compute, right? Instanton size is cut off, large instanton sizes are cut off by the inverse energies. So we are going to talk about small instantons. We're going to stay in the regime where the weak coupling, where the strong coupling, which ultimately will be dominated by the inverse instanton size. The strong coupling will stay relatively small. And at the same time, the overall total cross section we will find out in QCD will not be particularly small. So what plays the role of the Sphaleron barrier in QCD? So if I compare this result to what we had in the electroweak theory, well, that stuff actually was completely not taken into account in the leading order approximation, right? Instead of that, I had some v squared, rho squared plus rho bar squared, where v squared was the wave of the Higgs and gave rise to the Sphaleron. So effectively, in my picture, the Sphaleron, or something which emulates the Sphaleron, emerges from this term. And the scale which is present here is the scale of the partonic collision, right? So the Sphaleron, this effective Sphaleron, is becoming heavier and heavier when I increase the energy. So it's not fixed, it's becoming heavy and heavy and very large energy. This is a large contribution. So there are two ways. So another thing I have to mention is that this ubiquitous scale, the renormalization scale mu rho, which appeared in two different places. One, it appeared in the coupling, and the corresponding contributions of mu rho of mu r also appear in the instanton measure. And there is potentially a different scale mu r which occurred in these Mueller corrections, the hard rescattering events. So I'm going to set both of them to be the same. And I'm going to set both of them to be the same and equal to 1 over rho, right? So this is the choice. This is the choice of RG scale. So this is the choice of the RG scale. So that's the approach we are going to follow. So this is an approach which is very often followed in instanton calculations, and this is done in order to minimize the large factors in the pre-exponent here, rho mu, essentially rho mu to the power 2d0, which is a large effect. We also just to be on the safe side varied in our papers, varied this mu rho by a factor of 2, making it 2 times greater, 2 times smaller in order to estimate the theoretical uncertainty. And in fact, this does give rise, varying mu by a factor of 2 does give rise to some order of magnitude overall normalization correction. But I think we are in a state, this is not an NNLO perturbative QCD. We're in a state where theoretical normalization is not super well established. So the choice of the scale is one of the theoretical uncertainties in the calculation. Another place where theoretical uncertainties would come from are the effects of high order corrections to hard scatterings computed by Mueller before. And a third source of the uncertainty is the fact that one loop fluctuation determinant, so source of something where theoretical calculation should be improved, but wasn't so far, is that the top determinants, one loop fluctuation determinants around the instanton anti-instanton configuration were computed in the dilute limit, where the separation between instanton and anti-instanton was very large, right? So this is essentially what we've used is the for the top determinants, which is basically the product of one instanton and one anti-instanton determinants. Computing these determinants for not well separated instanton is a pain in the neck. I haven't tried to do it. On the other hand, I mentioned earlier that the actual values of the separation between instanton and anti-instanton are not particularly small. We'll see what they are. So perhaps this approximation is not terrible, but all in all, I would not be able to guarantee the normalization of the overall theoretical prediction to be, anything better than, let's say, 1 or 2 orders of magnitude. Okay, so in the first approach, so the paper with Frank Krauss and Matthias Schott. So Frank is my colleague in Durham, and Matthias Schott is an Atlas experimentalist. So we just computed all of these integrals using a saddle point approximation. Yeah, so this basically, there is a plus and a minus to this story. So the positive thing about using saddle point approximation, so basically just evaluating this whole integral using the steepest descent. So the good thing about it is that it's tractable, it's analytic, but you also can see where different, so what are the dominant points, what are the saddle points of all the relative parameters, relevant parameters. So for example, how large is the instanton separation, what are the instanton sizes, and so on. So this is a good thing. Alternatively, you could say, well, this is a saddle point approximation. Why shouldn't I just compute the whole integral numerically? After all, this is not a particularly terrible integral, right? It's an integral of, it's a multiple integral of all of these parameters. So, and that is what we've done in the second paper, where this integral is carried out numerically. So, but that is good. The results, the actual results are not very different from the saddle point approach, but what you lose is the understanding. When you just do these integrals numerically, you don't pinpoint the dominant values of separations and instanton sizes. Okay, so what we've got from the first approach is this. So this is the total partonic cross sections in picobarn as a function of partonic center of mass energy. And what you see is that unlike the electroweak case, the cross sections grow in the regime of small partonic energies, right? This is because this is the main reason for that is this hard quantum corrections resummed depend on the energy. So when you increase the energy, the exponential suppression of the whole thing increases, right? So while in electroweak theory, where these Mueller corrections were, I would say, incorrectly not taken into account at the time, right? They were known, but they were not really taken into account. And instead, the integral was cut off by the fixed wave of the Higgs field. The cross sections ended growing with energy. So here the cross sections dying with energy. But when the energy goes down, right, so this is 200 GeV. So I'm not talking about energies going to a sub-GeV scale. I would be really uncomfortable using instanton methods at 1 or even 5 GeV or even 10 GeV. So so I would not let my partonic energy become less than 20 or 30 GeV, yeah? As I mentioned earlier. You see that the total cross sections easily get to 10 to the 8, 10 to the 9 picobarn, which are huge. Yeah? So this is a relatively good story that we get very large partonic cross sections. Of course, we will need to turn them into hadronic cross sections and so on. The number of gluons in the final state is a function of square root of S prime. also grows. So you can see it basically at very low energies, it's small, but then at reasonable energies, it gets of order 10. So you're looking for states with 10, 12 gluons in the final state. Plus, you shouldn't forget to include, I mean, we should remember to include 2NF fermions in the final state. So we really are talking about a multi-particle final state configuration, and that is what would be used for phenomenology, yeah, to trigger on these events. Okay, this is how the instanton size is cut off. So inverse instanton size is a function of square root of S. And this is the alpha, right? So again, the alpha strong computed on the instanton, well, the alpha strong computed on the instanton size as a function of square root of S prime, well, becomes small at high energies and starts blowing up only at low energies, but I would never let it go to be larger than 0.4 or 0.35. Okay, these are some values of the cross section. So in the second approach, which is a paper which is covered by this thing, paper with Michael Spanovsky and my student Dan Milne, does all of these integrals numerically. So better to say does all integrations over all collective coordinates but one numerically. The one which is done analytically is the integration over the instanton separation, which is the mode which brings instantons and anti-instantons together. And it's in doing this integration, you need to do it analytically because you want to pick up the imaginary part. Okay. And so you basically, again, so the final results now from this approach. And now these are the cross sections and the numbers of gluons. Now again, okay, so still computed for different partonic energies. So let's say at 50 GeV, which is reasonably large partonic energies, you have cross sections of order 10 to the 3 picobarn. But let's say if you go to 500 GeV, you get 10 to the minus 3 picobarn. So then you turn it into a hadronic cross section. So you integrate. So now we have to integrate over Bjorken X for X1 and X2 for the two incoming gluons, right? And so normally you and then you basically would be able to probe the energies, the partonic energies. So here they are called as hat, from 0 to the energy of the proton-proton collider, right? I don't want to go to 0 because I will enter the regime which I can no longer trust my theory, yeah, because coupling constants will explode. I have no trust in instanton calculations at small energies. So I'm going to, so in this paper, we put a minimal allowed number, so minimal partonic energy at which we just cut off this integral, right? Abort the calculation, because we say maybe the contribution would be large from this from the theory prediction below as minimal, but I can simply no longer trust it. So to be on the safe side, I would just cut it off. So, and we usually cut it off at so we don't allow instantons. Sorry, we don't allow partonic energies, let's say, to be less than 30 GeV. Okay. Good. So I'm getting to the end now. So one thing where, okay, so all very good. So there are some uncertainties coming when we enter the infrared regime, but I don't want to enter the infrared regime. I can also select experimental cut, so put on selection rules on the final state in order to make sure that I do not go to this regime. Yeah. But so cross sections are large. This is all very good. But so how do I distinguish them still from multi-particle QCD backgrounds, right? So one idea would have been to allow to say that there is one that there is at least one jet in the final state from this instanton process, which is very energetic, right? So you would want to put on a jet with a large Q squared. Unfortunately, this immediately introduces an instanton form factor. So it would be an effect in the exponent e to the minus q rho plus rho bar, where this is the q. And so if you make this q to be well, sufficiently large, yeah, 300 GeV, for example, right? The total cross section drops to 10 to the minus 23 picobarn. So you have no way of triggering on the instanton effects by saying that I have one or more high PT jets, as well as a spherically symmetric final state. Just doesn't work, immediately kills the instanton. So these are conclusions. So QCD instanton cross sections can be very large at Hadron colliders, still within a controlled approximation. Instanton effects are isotropic multiparticle final state. So the event topology is very distinct. So in the event shape variables to trigger on these instanton events, right, we used sphericity and jet broadening event shape variables to select these events, right, and also count the number of final states, asking for a large multiparticle final states. If we try to trigger on instanton events with a large PT, they dramatically kill the cross section, and so this is not the way. So essentially, in order to make progress with how to discover the instantons that exist in future colliders, Hadron colliders, if we ever get future Hadron colliders, is to consider alternative triggering processes in the final state. So one promising idea is to consider instanton production in diffractive processes. So I ran out of time. I won't talk very much about it, but that's started being investigated. Okay. So single diffractive and double diffractive processes. Okay. So that's basically the end of the talk. So I wanted to basically emphasize the fact that perhaps against naive, intuitive expectations, the cross sections for processes generated by instantons, by QCD instantons created in Hadron collisions are not small, they are large, right? So, but if you ask the question, why haven't these effects been discovered before? At Hera, well, Hera was a different story. It was deep inelastic scattering, but falls in the same category. At Tevatron, at the LHC, well, it is looking for these processes and distinguishing them from QCD backgrounds, which is where things become very complicated. So I would say that even though the instanton cross sections are large, and this is a good thing, the fact that instantons have not been seen so far at colliders is totally not surprising. I would have been very surprised if they were seen. And so more work is needed to figure out how to do it in the right way. And as soon as you start putting in complicated selections on the final state, going to single and double diffractive processes, you dramatically cut on the signal. Okay, so thanks very much.
Thank you, Valya.